Hello. Okay, so lots of people in the room, so that's gonna be just as for me to understand. How many people are here and never attended this conference before, or any Erlang conference for the matter? Okay. How many people have never written a line of Erlang? Okay. How many people have never written a line of Elixir? How many people have written a significant amount of Perl? Yeah, I see at least one. Okay. Okay. So this talk, which is was originally called Idiomatic Elixir, and as I was working through it, just changed the name because it felt like I was not going anywhere with this. So actually, what ended up being more interesting for me to talk about is the idea of flexible Elixir. So as you would expect, let's start from the definition of flexible. So flexible is something that can change depending on the situation. And in the case of a piece of software or a programming language, we could think about requirements or pretty much things that we didn't know about the problem we're trying to solve that just surface as we walk through it. But doing that means being able to do that without breaking. So more often than not, we find ourselves in the situation that we start to build software, we have all the best intentions, and we really want to make it easy for this software to change over time. But as we try to do that, things just explode and the complexity just grows, and it becomes very difficult to be able to maintain that flexibility. So, maintenance grows, iteration speed goes very high. So in the end, all of this becomes a big problem. So the idea with this talk, and we'll do it through code examples, is to navigate through three basic ways of using the language. And there's going to be a lot of overlap with things you can do with Erlang as well. So it is Elixir specific, but there's things that you can use in Erlang as well to see how we can maintain that flexibility. Now, if you are at the beginning of your learning process with Elixir or Erlang, there may be things that may be useful for you. If you are a very experienced developer, I would recommend to look at these things from the perspective of helping out someone who's learning. All these examples come from the fact of talking to people that are learning the language and things sometimes they get stuck into. So it may be useful just to see how you can help out these people to unblock over time. So just keeping maybe a couple of perspectives at the same time. So the first use case is handling volatile data. So handling volatile data, which is a very generic term, in our case means working on a cache store. Now, this is and a key value cache store is one of the textbook examples of things that people build with Erlang and Elixir as they go through it, particularly when they start to talk about processes. Because it's a fairly contained API, and it's fairly straightforward to understand. So our key value store in the example is very simple. It just has get and set, and it doesn't have expiries, it doesn't have TTLs, and essentially you can put anything into it. So we're not going to worry too much about what actually goes into it. But the important bit to remember is that it will be backed by a process. So we will start to introduce the idea of using processes to build something like this. That's why you can start it. Now, in the Elixir world, there's a lot of emphasis on using agents for these kind of things. If you just make a very simple research on the web on how people build this type of key value stores, agent comes to mind first. So an agent is effectively an abstraction on top of a gen server. So an agent is a process that in a completely sequential fashion, so one message at a time, has an API to hold a certain piece of state. The shape of the state is completely arbitrary. You can just use whatever you like. And then it offers primitives to get, set, and update. It's normally used to store a state that doesn't need to be accessed with an extremely high frequency because it is one process. So by definition, it is a bottleneck. So to use it, as you can see, the API is very straightforward, very short. You basically use callback functions for everything. So in terms of implementation, it has the benefit of being clear and it fits. I mean, just because the slides have to be, like, the font has to be big. But this is just less than 40 lines of code. So it's simple because you can keep it in your head. It's also strictly consistent because it does one thing at a time. Even when you want to update and read, it offers an API to make sure that that happens in the right order. But that becomes also the drawback. In our example of a cache store, having one process that does that it's not going to end up well under a load test scenario because you will have a message queue that grows until basically the entire node explodes. And as it's in-memory data in that process, if it crashes, the data is lost. Now, the recommendation is not to do much in the functions you pass to it, so it's very unlikely to break. But in the end, the risk is still there. So when people investigate improvements over this, they end up working on a combination of GenServer and ETS. So GenServer is a primitive to, I should say a behavior more than a primitive, to model a client-server relationship. So as a process that interacts with another process, I'm a client, the other process is a server, I can send messages to the other process that conform to a certain grammar, to a certain API, and I can basically either execute commands and get results or simply execute side effects on the other process. It's so generic that you can use it to model pretty much anything and use it as a building block to model all sorts of other things. And the server defines how these mutations and this data works, but it's also the base of implementing agents. So effectively, you're going from a specialized implementation with an agent to a more generic one with a GenServer where you can do more things. ETS, which is the other idea that we're going to bring into places, Erlang term storage, is effectively a key value store built in the standard library that can be used with different properties in terms of uniqueness and performance and access of the data. It can hold very large data, Erlang terms, so it doesn't have you don't serialize data in and out of it. It just can hold just the data you put into it. And it offers like interesting properties like constant time access. So it makes it ideal for a scenario where you want to build a cache store because you can. It does have the property of being very fast in looking up the information you need. So if we start replacing the agent implementation with an ETS table, then we can start to optimize around the use case of performance particularly. So if we put our table as a table that can be read by any other process with a public access, and we optimize it for reading, so we basically twist some knobs in the table configuration so that long bursts of reading operations remain really fast compared to writing, which is most likely the scenario of a cache store. Like you don't write that much, but you read way more often. Then we can completely reverse the perspective in terms of how we handle the pressure on this cache store. Because while we still write going through the GenServer, and you may or may not do that, but this way you just write at basically a sort of like a predictable pace, one message at a time. But then when you read directly from the table. So instead of going to the GenServer and essentially keep that GenServer business, you move the reading operation to the calling process. So that gives you the back pressure you need, and hopefully you will not suffer too much for it. But you basically optimize so that more processes can read at the same time without the problem of having to wait for the GenServer to be free and take charge of the request. So you get good, properly concurrent writes and reads. You introduce a slightly, you're switching from strict consistency to eventual consistency, because if writes are queued, and then if the GenServer is busy and is still waiting to write, and you read, you may read something that will be outdated by the time you reach the last message in the GenServer. But as it's a cache store, it may not be a huge problem. But depending on the use case, this may be a deal breaker. Again, we have the same problem. As the table is owned by the GenServer, if that GenServer crashes, the data is gone. So to solve this last problem, we can think about the data from the point of view of the application. So we expose an API in the cache store to create that table, and we move that operation to the top-level application. Now, it doesn't need to be necessarily the top-level application, but that just means that we are making the explicit choice of saying that data, it is volatile, but I don't want it to go away, and this way, it will go away only if the entire node crashes, which in comparison seems like a much bigger problem to worry about. So at that point, I guess the cache data is not that important. So you basically have only one possible event that can cause that data to disappear. And the reason why this may matter is because while the data itself may not be important in the cache store, the computation needed to repopulate the cache may be extremely heavy, depending on the use case. So in the case of, for example, a recovery after a crash or a sort of like disaster in the app, a influx of computation that has to repopulate the cache may actually be a worse problem than the crash itself. So this way, we somewhat like try to avoid that. So the second use case is around expensive operations. Now, this is, again, it starts from the idea of starting from a basic use of Gen server, which we're going to use to implement some sort of bucket. Like a bucket represents a process that we can use to save data to a remote location. So the expensive operation we're going to focus on in save data to a remote location, which is network and all of the problems that it can imply. So a Gen server implementation, and this is like code that sometimes you definitely see, is we want to save the data remotely, but we also want to know that that operation has been done. But the code written like this has one specific problem, which is you are basically waiting for the operation to finish to return essentially the caller is blocked until this happens. But it's a bit of a red herring, because actually what you can see from the code is that you don't really care about or rather, it seems that you care about the return value of that operation because your pattern match gone okay, but the result of that doesn't really matter because you're returning a static value. So what happens under the hood, and when you talk to people about this, is that what they actually sometimes they care about is not the fact that the operation is successful at this point in time, but rather that the operation has started. So this works, but the bucket is blocked while it's saving. The caller is blocked. Pretty much everyone is waiting. And if you fail to sync, the bucket itself dies because that pattern match clause will cause the bucket to crash. So we can start to work around the first problem, which is how do you acknowledge the work being done while not blocking the caller? First thing you can do is that if you just really care about a confirmation, you can definitely still use a handle call, so you can definitely block, but reply straight away to the client saying, I know what I'm doing, this work will be done, and then after that, you start to work with the remote source. So this way, the caller is unblocked, and you have the guarantee that you know that by the time this call returns, you know that the work will be executed. It's in the process of being executed. So the caller is unblocked, and it has the same guarantees, meaning if you just care about that, you have that, you know that that's going to happen. Now, sorry, this doesn't have anything to do. But the problem with that is that now, for that operation, which is a one-off operation, we are blocking the Gen server for no specific reason. So, and this is where you may have different solutions, but at that point, as you're free to do that computation somewhere else, you can decide to move that computation from the Gen server to another place. And that could be anything from spawning a process or using a sort of like a bound amount of processes, like a controlled pool. There are different techniques for that, but in the end, there's no specific reason why that computation should happen there. The only thing you care about is that if it fails, you just know about it. So the bucket is unblocked, and that way we just get a nice compromise. Now, the third use case is about what I call essentially functional pipelines. Now, this is Elixir specific. The two first use cases, you can definitely do the same thing in Erlang. But functional pipelines is a specific thing that Elixir provides compared to the constructs available in Erlang. So if you want to digest user input, let's say you have some incoming data, you want to whitelist the data, you want to do some validations and save it. Each step along these lines may fail, meaning each step can return an error, and you care about that. But at the end of it, you want to have a value. You want to return a value that represents either the success of all of this pipeline or any error halfway through. Like a pure pipeline, which is like one of the things that you see normally when you look at a lot of Elixir examples, uses a pipeline that uses the pipe operator. And the assumption that this code makes is that each step returns a value that can be piped straight into the following function, because the pipeline operator is just an operator that takes the return value of the previous function and passes it as a first argument in the subsequent function. So you can just use it to basically unroll a nested function call. But there are a few problems with this, because what if you don't return a value and you return an error? At that point, you got an argument error because there's no pattern matching between the two functions, and everything crashes miserably. And the only option you have at that point, especially if you're doing this and it's wrapped by, for example, in this case, it's a hypothetical controller, but if you think about it in a request process, the only thing you do is put like a massive catch-all around it, rescue any type of exception or error, and return possibly a 500 to the user, which may not be ideal. So what you want in this case, or what could be more desirable, is making sure that, yes, we want something that works for the golden path, but we don't want anything that fails with argument errors because it's just difficult to manage. So you can try to use a try and rescue, which is a slightly different. Try and rescue handles specifically exceptions in Elixir, where you have the ability to try a computation and rescue a specific exception. So you pattern match on the exception being thrown, and if you rescue it, then you can return a value. Anything else will just keep erroring, so the process will crash. But it's like it's a bit of a shotgun approach. Like you just like shoot a massive, like you just put a massive net underneath, and then you just hide any error into it. Now, it could be useful to protect the entirety of your request cycle, but it may not be useful to actually understand what's happening. And more than that, you're rescuing, therefore you're hiding all potential errors. So all failures in this approach are treated the same way. There's zero difference between them. There's something that is better. There is just a much better approach with this, which is the usage of a with macro. Now, the with macro is like a supercharged version of a combination between a pattern matching and the pipe operator. But the way you read that statement, with, is you start from the top right, and if the computation on the right returns something that matches on the left, you go to the subsequent line on the right and do the same thing. So you just keep going, zigzagging, right to left, right to left. If at any point a pattern matching clause doesn't match, you would drop directly into the else branch, where you're going to get the value that didn't match. You can pattern match on it and return whatever you need. So this means that as long as we have some sort of consistent way to return values from those functions, which doesn't need to be OK and error. That's completely arbitrary. You can pattern match any way you like on the left-hand side. But you still get the benefit of a list of steps that you can read from top to bottom, with the knowledge that at any point in time you can just shortcut if there's an error underneath and handle that with the specificity that you may need So you express, the intent is very clear. You clearly express what can fail. And you definitely have a fine-grained level of control over all of the failure cases. Because in the end, exceptions are different from errors. Some exceptions represent things that really, the best thing you can do is just like back off and crash. And that's kind of like the basic approach in terms of error handling that we have in the community. But that doesn't always apply, because sometimes you want to know what that error is, because you need to give something back to the user or to the more external layer that wraps this computation. You do need to start to, if it's not possible, to tag some of the return values, simply because if you just have, for example, an integer that comes back, it may be easier to wrap it into a tuple to make sure that you express the fact that it's a positive result. So this was like sort of like a ride in 3 use cases, but the idea was around flexibility. So the flexibility means we went through different use cases where we gradually increased the complexity of the code. We increased the number of moving parts in some cases, because we ended up tackling requirements one by one until we reached to a solution that is still manageable, but it has sometimes completely different properties from the initial one. But the amount of code needed to do this was very small. So we can do this incrementally without having to necessarily impact that much all of the other parts of the code that work together with the one that we are working with. Things to, or like ideas that can come out of this is that, first of all of the things you've seen are in the standard library for Elixir Erlang. So taking some time to look at the standard library, it may be useful. There's definitely a lot of modules that you may end up never using, but some of them are particularly powerful. And the rest is just about making choices. This is more for something when you're at the beginning of your learning. It's very easy to forget that Erlang and Elixir put a lot of emphasis into taking decisions about, for example, who owns the data. The example of the ETS table was particularly related to this, because the process who spawns the table owns the table, and there are definitely things you can do about that, but it wouldn't be necessarily obvious unless you know that there's that relationship. But it's important to remember about that. So who owns the data may determine particularly scenarios of failure and recovery in the application. And also making explicit choices about who runs functions, particularly in web applications where we have a request stack. Sometimes there's a tendency of doing everything into the request process, even if you split it down to multiple files, but at the end of the day, is still happening inside the request process. And they may not be desirable, because it just means that maybe you're doing more computation than needed inside that single process. And finally, it's important to start by saying let's just write the basic use case and let everything crash. But after that, making explicit choices about what kind of failures you wanna have in your code may be very beneficial, and that's something that can be done over time. You don't necessarily, it doesn't make a lot of sense trying to predict everything that can go wrong. That's exactly the opposite scenario that we want to go for. But sometimes paying a bit more attention around how failure happens may actually lead to more usable APIs and easier integration with the other layers of our system. So thank you. And if you, definitely take questions now, but if you have any other question or anything like that and you want to reach me afterwards, these are my coordinates, which I hope they are visible at the end of the room. Yeah, okay, I get positive feedback. Yeah, all right, thank you.
So in the first use case where you're doing the cache store and you said several clients can read the same piece of memory, can they read while the memory is also being written to?
Yeah, but they may, if it's being written, yeah, Yeah, yeah. That doesn't block. That's the point. That's the point. Like reads and writes happen concurrently.
So if I'm storing a large value, not an integer or primitive type, something very large, is there some locking going on underneath between the writers and the readers that prevents the readers from reading while the writer is writing?
Let me think about it. I think by default you may get a stale copy.
Okay.
You may get a stale copy. It depends on how fast that operation happens, if it's still happening. But you may get a stale copy. But I think these kind of things that you can tweak them.
You talked about the simple approach of using the agent in the cache store example.
Mm-hmm.
But there's certainly limitations to that. Is there any real place you feel for the agent construction besides just sort of a simple teaching?
For example, in this case, we were basically working with like the cache store was a sort of singleton, right? You got one of these with a name in the entirety of the application. What if you had, for example, let's say you do many things. I don't know. Let's say you're making a game. I'm just like throwing it out there, and then you want to keep a specific state for each person who's playing the game, and that state is only accessed by that person, and the amount of reads and writes that person can do is limited. Then you could potentially do that, but realistically. It is normally used to hold some configuration data, some specific pieces of data that don't have a very high frequency of operations, because otherwise it becomes just a bottleneck. There is a place for it, but the moment you get over a certain level of complexity, you may end up swapping it for a gen server. It depends on how complex it gets.
Right. So just a tiny comment on the first use case. Once you moved the ETS table creation from the process to the supervisor, I think it is.
Yeah.
Sorry, Erlang programmer here.
Yeah.
So, yeah. When you move that there, it only works because it's a public table, right?
Yeah.
If it's a protected one, you have to use inheritance or other mechanism.
Yeah, yeah, yeah. So I'll just like show it because it's actually a very good. So just get in there. Yeah. So what Brujo is referring to is the public flag that makes the table. It makes it possible for the table to be accessed by any other process. So that means that it's also potentially something that you need to think about if you have data that you don't want it to be accessible from other places in the application.
Any other questions? One more. Okay.
So for the with flows, is there any advantage of using that versus like doing like explicit pattern matching when you're like defining like the functions, right? The pipeline example. So like in the functions instance, it's an example, but in the functions, right, you would basically want to check the parameters and say like, okay, if I see an error here, just pass it along and don't do anything, right?
Mm-hmm.
In this case, the pipe still works, right? So
Yeah.
is there like any advantage, like performance or other type of advantage of doing the width?
It's more about just not having to write two function heads for each function. Like, so for example, let's assume that the whitelist function returns OK with the params and error reason. That means that if you did it just with a pipe, you would need to write a version of validate that accepts OK value error reason. And that becomes a pain after a while, because it forces you to have like ad hoc shapes for each function, and it makes it difficult to compose effectively after a while. Like if it's like 5 or 6 steps, it gets unwieldy. So this way you basically just write one version of the function and then return just that.
Anyone else? We still have some time. Okay.
So basically, you write every state into the table. Is that correct? In the ETS table?
Every key value, yeah.
Right. So eventually the table grows, and if the process crashes, it basically has to read from the huge table. I'm not sure whether there will be like, if I have millions of billions of state coming in, and it is recorded in the table state, will it be will there be a problem with the performance issues, like reading a particular state because there's a huge data?
I mean, if an ETS table gets over a certain size, which is like, it depends how you use it, but it can be a variable number, then at that point, you may need to change that table with something else. Like there are different options around that. Particularly, you can shard the table. There's actually there's a project that is it Carlos that does the shards, the shards project. I forgot. Yeah. So it's basically there are implementations that you can use, for example, to take this data and then split it into different tables in order to get back, basically by partitioning you get back performance. But realistically, you just want to profile that first before it's a problem. But yeah, most of the times you're just memory bound, and that could be the case. But there is that's mostly the case, yeah.
Okay, thank you.
Yeah.
One last question.
In that side, can you use that in Will?
I think so. Yeah. Yeah.
Okay. Thank you very much, and please help me thank the speaker.
Thank you.
It seems we're a bit ahead of time, which is good because now there is the lunch break. So rush to not be queuing.
Please remember that when you rate the talk, remember that you're going to lunch earlier because of the talk.